Hello everyone and welcome to MV Tutors. I'm Sol and I'll be looking at question 1 with you guys for paper 2 physical science. So basically looking at chemistry as our paper 2, and do not forget to like our videos as well as subscribe to our channel. Do tell your classmates about this channel. There are many others, but if you love the way we explain things, do tune in. All right. So we're gonna start with with organic chemistry. Let me just make this a bit bigger so that we can see what's going on and read properly. All right, so this is where you should bank your marks. Don't just guess. Take the time to do so. Remember, if you want to know how much time you must spend on a question, this paper is out of, or was out of, 150 marks, okay, and 3 hours allocated to it. So if you want to know how much time to spend on it, you're going to tell yourself, okay, fine, I have 150 marks, I have 3 hours. 3 hours is like how many minutes now? 180 minutes divided by 150 marks. So on each question, I should be spending roughly 1 minute 1.2 minutes. 1 minute, that too does not present 20 seconds, no. So 1.2 minutes per question. So if a question is out of 20, you should be spending about 24 minutes on question 1. So time yourself. Can I time myself? Well, I'll be explaining, so I might take more. But let's say 24 minutes, we should be done with this question. Let's see how we do with that. Okay. And if you're not done by 24 minutes, move on. Go to other questions that you know you do well in, so that you don't get to a point where they say 5 minutes left and you see questions that you know and you're like, I should have just, or I shouldn't have, or I could have. Prelims are tight. So as you prepare, please also prepare your time as well. Time yourself. Do not think you have the luxury of time. Okay. So now 1.1. The compound with the hydroxyl group is, remember this is the hydroxyl group, and the hydroxyl group really with organic chemistry refers to organic compounds. So when I see sodium hydroxide, I get a little bit excited because I see hydroxide there, but that's not a hydroxyl group. So I move on. The second compound, I see Cu. If you see COOH, you know you're dealing with a carboxylic acid, so move right along. C, I see an OH there and I get excited and then I'm like, yes, that has to be the one, right? Because D, there's only one O and it's at the end. Okay, so that's an aldehyde, probably. All right, so C, yes, compound with a hydroxyl group for 1.1. 1.2, which of the following compounds represents the first member of the ketones? Now remember, an aldehyde and a ketone, they're isomers of each other, right? Functional isomers. With an aldehyde, the double bond to oxygen is at the end, okay? Whereas with the ketone, the double bond to oxygen is somewhere in between the carbon atoms at the end. Okay, so the carbon, sorry, my nose is just so itchy, so I'll be scratching it throughout this lesson. All right, so yes, ketone, somewhere in between, aldehyde at the ends. So let's see. Of A, I see we have one carbon, and it's double bonded to, so we have something like this. What am I doing? H and H. Okay, so no, this is not a ketone we're looking for. And then B, I see an OH, so we're looking at an alcohol there. C, I see an oxygen somewhere in the middle. Okay, so we have carbon, 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 1, 2, 3, 1, 2, 3, double bond. Yeah, this looks like a good candidate, right? Yes, so C, yes. D, Cu, carboxylic acid, will not work. So again, C is the answer that we're going with. 1.3, which of the following compounds has the highest boiling point? Remember, the longest chain will have the highest boiling point. The branched chain compared to the longest chains, provided they have the same number of carbons, that will not have the highest boiling point. So the more branched a compound is, the lower the boiling point starts getting. So let's see now the options that we have. So for the first option, we have 2 carbons. Okay. B, we have 1 plus 4 plus 1, we have 6 carbons. Okay, so for now, I'm just counting the carbons. Okay, so A, we have 2. B, we have 6, so B is winning so far. C, we have 1, 2, 3, 4. So B is still winning. And D, we have 1, 2, 3, 4, 5. We have 5, but this D is a straight chain. Okay, so it looks like this: 1, 2, 3, 4, 5. Okay, and we have our 3 hydrogens there. So everything is just single bonded. There's no double bond. So that's D. What happens with B? Before we complete that B is the answer. So what happens with B is we have 1 carbon, and then we have oh, actually it is also a straight chain. I thought it was a branch. No, it's a straight chain. They didn't want to write. It's a condensed formula. Okay, so clearly this one takes. I thought it was a branch. So 1, 2, 3, 4, 5, 6. Okay, clearly B takes the crown. I mean, it's a straight chain compared to D with 5 carbons. B would be the correct answer here. Okay, I really thought it was a branch. Now 1.4. When CH3 is converted to CH2, so basically you're moving from a single bond to a double bond. The type of reaction is, what did we do? We just eliminated 2 hydrogens, right? Now we're left with 4 for this double bond. Okay, so elimination reaction. But what type of elimination reaction is it? Is it A, dehydration? Dehydration means you are removing water. Okay, you are dehydrating it. It's going to be thirsty. So no, we're not removing water, we're removing just hydrogen. Okay, H2. And then dehalogenation. So a halogen, remember, it is hydrogen with sorry, a halogen is in group 7. So your chlorine, iodine, all the enes, fluorine, and all of that. So dehalogenation, no, we don't have any halogen in our compound. Substitution, no. If it was substituted, you would still have single bonds. Now dehydrogenation, yes, we removed a hydrogen, dehydrogenated it. So D is what would be the right answer that we are going with. And then, now that we talked about dehydration, I feel so thirsty and I'm actually hungry. So let's do this. Let's finish this. Which of the following changes will increase the rate of production of hydrogen gas in the reaction below? So we have our solid magnesium, aqueous sulfuric acid, and then magnesium sulfate, your salt and aqueous solution, and your hydrogen gas. So what would happen if you were to increase the pressure by decreasing the volume? So an increase in pressure obviously is a decrease in volume. And if you have an increase in pressure, look at the number of moles, which are the most, the least number of moles, but gas only applies. So we only see gas in the product side. So if you increase the pressure, well, there's only one thing to look at, which is your hydrogen gas. Yeah, so will it increase the rate of production? Let's hold that thought. We have nothing to compare it with. Okay. B, add water to the reaction mixture. Okay, so if you add water, you're adding H2O. All right. So if you're adding to the reactants, Le Chatelier comes in and says, to counteract it, we need to also increase on the product side. So, okay, I see you. Let's see more options that we have there. Increase the volume of H2SO4. Increase in volume, decrease in pressure, but we don't really have gases to compare with this. So No, we're not really doing much there. Increase in volume, decrease in pressure. Again, it only applies to the hydrogen gas. Um, and if you have a decrease in pressure, you're going to look at the most moles. But like I said, you only have hydrogen to compare with. So it's also on the fence with that. Or actually, I'm more inclined to say no. D, increase the concentration of sulfuric acid. So if you increase the concentration, now that I think about it, add water to the reaction mixture. Water is a liquid, so I don't think it has much of an effect. So B and C were canceling. A will bit on the fence. D, increase the concentration of sulfuric acid. So there, if you increase the concentration of a reactant, Le Chatelier comes in and is like, hey, you need to balance things up. So we need to increase on the product side. And if you increase the concentration on the product side, you're looking at your hydrogen that would increase as well. So the rate of production would increase. Oh yes, the rate of production, not just the production, but also the rate of production of, yeah, so concentration will definitely do the things. Okay, so I'll go with 1.5 D. All right, we're halfway there. So now let's see what 1.6 has in store for us. So that was the rate of production. Remember what influences the rate of reactions. Yeah. So 1.6, consider the following reversible reaction. So we have 3Y2 and then 2Y3. Okay, so it's balanced. And then if the activation energy for the reverse reaction is 180, remember this enthalpy says we have a negative 80. So this is a exothermic reaction, an exothermic reaction. So if the activation energy for the reverse reaction is 180, so going this way is 180. Why am I putting degrees? Thinking about math. So we have 180 kilojoules going in the reverse. And now the activation energy for the forward reaction, what do we need in the forward in order to result in negative 80? I say, if I'm just doing maths straightforward, you need 100 because 100 minus 180 will give you negative 80 kilojoules. Okay, so I would go with 100, which is option C. And then 1.7. So consider the gas phase equilibrium system represented by the following equation. So you have 2 moles of water, and you have 2 moles of hydrogen gas and 1 mole of oxygen gas. And the whole thing is the enthalpy is bigger than 0, meaning that you have an endothermic reaction. Okay, so which of the following changes will decrease the equilibrium amount of H2O? Okay, so we want a decrease in the reactants. That's basically what they're saying. So what happens if you decrease the volume of the container at constant temperature? Okay, I'm glad we have gases only this time. So decreasing the volume will increase the pressure, and therefore we're looking for the least number of moles. Okay, and if we look there, and on our reactant side, we have 2 moles. On our product side, we have 3 moles. So a decrease in volume, we're going to look at the least number of moles. So it'll be on the reactant side. So basically, it will increase the reactants. And that's not what we want. We want a decrease. Okay, so A is out. B, adding more oxygen. So we are adding oxygen. Okay, so according to Le Chatelier, if we add oxygen, we need to counteract it by adding, to counteract it and find the new equilibrium, H2O will increase. So we're increasing reactants again, and that's not what we want. C, adding a catalyst. Remember, adding a catalyst only deals with the rate of reaction. It just speeds up the reaction. It doesn't really give you a higher yield. It's just an increase. Okay, so C, no. And D, increasing the temperature at constant pressure. Okay, So if we're going to increase temperature, remember an increase in temperature favors the endothermic reaction. And so endo is favored. So we do have an endothermic reaction as is, right? So if then the endothermic reaction is favored, it means your products will increase, okay? Therefore, we will have a decrease in H2O. So D has to be the right answer. If D was wrong, then geez, we have to go back to all of the options and read them again thoroughly. Okay, 1.8. The following equilibrium constant expression is given for a hypothetical reaction. Guys, I don't know why my nose is so itchy, but it's so itchy. Okay, and it's right here, not even anywhere else. So the following equilibrium constant expression is given for a hypothetical reaction. So yeah, Kc, remember you have products divided by reactants. So for which of the following reactions is the above expression of Kc correct? So like I said, it's products over reactants. So I will start with x3y8 to the power 1. Okay, so we put a 1 in front, but we don't really put it. And then we have plus z2 to the power 5, so that's what it is. And then we have y2z and a 4 in front plus x z base 2 and then a 3 in front. So what is there? I see x3 y8 as a, b and c are cancelled out, so I'm comparing a and d, okay, because they have x3 and y8. Now 5z2, okay, so a is winning, d as well. Now let's get to the product side. 4y2z, okay, so a looks correct. Let's look at d. 3, no, so they have 3 here instead of 4 and 4 instead of 3. So a 1.8 a is the correct answer. And then 1.9 HP04 2 minus can act as an amphelite. Remember, an amphelite can be an acid or a base. In which of the following reactions does HPO4 2 minus act as a Bronsted-Lowry acid? Okay, so if it's going to act like an acid or act as an acid, actually, it will donate H, right? Because acids donate and bases acid, okay, donate H atoms. If you're an acid and then if you're a base, you will accept. So let's see. We're going to look on the reactant side and look on the product side where we have the least amount of H, okay? So if I look at A, HPO4 2 minus plus H2, no, so it gained, so no. HPO4 for B plus H, the same, nothing really happened. HPO4, now I'm looking at C plus H2O, PO4 3 minus, and H3O. So here C is a likely candidate because we can see that it donated one of its hydrogens. So let's check with D first. So HPO4 2 minus plus H2O, and we have H2. So here it gained an H atom, so no. So C is the answer that we're going with. And we are almost there. I wonder, are we within 24 minutes? Which of the following weak acids, each of concentration 0.1 mole per cubic decimeters, has the lowest H3O concentration? So weak acid will have a very low H3O. And I think you just need to look at the K. It also corresponds with the Ka value. If it's a weak acid, your Ka value will also be quite low. Okay, so let's see. So H2SO3, I'm expecting SO4 is sulfuric acid, SO3 I think it's sulfurous acid, I'm not sure, but that should be a strong acid. And then also, which one? H2S, okay, no, clearly it's not that strong. So the strong acids that I have here is H2SO3 as well as Cu, your carboxylic acid. All right, so, and how do I know that those are strong? Because the exponent is -2. okay, which is bigger than -7. So we're going to look at options B and D. Okay, so we have -10 to the power -7 for both, but 4.2 is bigger, right, than 1. So the one with the weakest or has the lowest H3O would be D. Okay, so our final answer then for 1.10 would be D. And this is where we end off question 1. I'll have a look after recording this if I am within 24 minutes. Please work on your speed, but try to work as accurately as possible, because with speed sometimes comes silly errors. Okay, but yeah, thank you for tuning in. Hello everyone and welcome to MB Tutors. I'm Salo and we are continuing with the chemistry paper. We'll look at question 2. Organic compounds. Quite loaded. So this is still the June exam written in the Gauteng province. Okay, don't forget to like our videos and also subscribe to our channel. Let's get to it with question 2. So we have letters A to F in the table below representing 6 organic compounds. So what I like doing, I just like taking time to see what these compounds are, which functional group they belong to. Can I name them? If they haven't given me the name, can I draw the structure or formula if I've been given the name, and so forth. Okay, so let's try that, and hopefully the rest of the questions will be a breeze. Hopefully. So with the first one, A, I see that I have an alkane because this is just a hydrocarbon with single bonds. Okay, so it's an alkane. What type of alkane is it? It's going to count the amount of carbon atoms. So I have 1, 2, 3, 4, 5, 6, 7, 8. So that's just going to be octane. All right, remember it has, with alkanes, you have H, CH, CN, what am I saying? CN and H2N plus 2. So you're expecting, if there are 8 carbons, you're expecting 18 hydrogen atoms. And then with B, okay, the longest chain, which is the longest chain? If I start from here, I have 1, 2, 3, 4, 5. Okay, cool. Let's see if I start from there. I have 1, 2, 3, 4, 5, 6. So 6 is definitely the way to go. All right, because look at the longest chain. But where are we starting? Are we starting from left to right, or are we starting from right to left? Or because we see the double bond, do we rather start there just to be safe? So 1, 2, 3, 4, 5, 6. I say let's go with that double bond first, né? And if that's the case, we then have carbon 1, carbon 2. At carbon 2, we have this methyl group, and then we go carbon 3, carbon 4. We have another methyl group, carbon 5, carbon 6. So I would say at carbon 2, as well as carbon 4, we have a methyl group, right? So 2, 4, dimethyl, because there are 2 of them. So dimethyl, 2, 4, dimethyl. And because we have 6 carbons, it is hex. And because it's a double bond, we have, it comes from the alkene group. Okay, so yeah, dimethyl, hex. On the first carbon, that's where we have the double bond, so hex 1-ene. And remember, this is just extra information. The general formula would be CnH2n. Okay, if you don't believe me, just go count the number of carbons. You know that there are a lot of them, and then count the amount of hydrogens. You'll see the hydrogen atom would be twice the number of carbon atoms. Okay, so that's B. And then C, we have C3. So I'm just going to draw the structural formula. H7, so 1, 2, 3, 4, 5, 6, 7. Then we have a chlorine, and we don't know where this chlorine is positioned. I mean, it could be on the first carbon. Remember, the first carbon, reading from left to right, is this one. Going from right to left, it could be this one. Okay, so you either have the carbon at the end, or sorry, the chlorine at the ends, or you have the chlorine in the middle. We don't know the position. Okay, but what I can tell you is because we have a it almost became an alkane, but because there's a halogen, it's a haloalkane. Okay, so we know it's a haloalkane, but because we're not sure of the position of the chlorine, we're just gonna say we have chloro, and because we have 3 carbon atoms, chloropropane. Where is the chlorine? It could be on position number 1 or 2. So for now, let's not even talk about positions. If they do ask the question, they will give us more information to tell us the position of the chlorine. And D, we have propanoic acid. So prop means we have 3 carbons. And if it's acid, oic acid, we know that we have carboxylic acid. So we must have Cu. All right. I'm not going to put the hydrogen atoms. It's going to take us forever. So we can see there's propanoic acid, 3 carbons, and Cu at the end. Then E, we have pentanol. Pent meaning we have 5 carbon atoms. And al meaning that it is an aldehyde. With an aldehyde, your oxygen group is basically at the end. At the end meaning it could occupy the first carbon or occupy the last carbon depending on where you are starting to count. Okay, I normally like putting it on the right hand side. So your double bond to your carbon, double bond to oxygen would be there. All right, and you just put the other hydrogens where they're supposed to be. So now F, the last one. So this takes time, but like I said, hopefully it will make the other questions answering it go much quicker. So if we have Cn, H2n, O2. Okay, so they've given us the molecular formula. We don't know what this is. I mean, if I see 2 oxygen atoms, I know that it could either be a carboxylic acid or an ester. But the trick with those is in the general formula, you have 2n plus 1. Okay, so at this moment, we don't know what this organic compound is. If you do know, you can comment down below. And yeah, I think we can go on and answer these questions. Okay, we have analyzed what we have. It should go down, quite easily, I hope. So now we get 2.1 where it asks, define the term unsaturated hydrocarbon. Okay, so if it's unsaturated, it means you either have a double bond or a triple bond. Okay, we've never had 4 bonds. So double bond or triple bond. So unsaturated means you can still, loosely defined, you can still add more to it. You can break the double bond or the triple bond, and add onto it for it to ultimately become saturated, meaning you can't add any more hydrogen compounds or any hydrogen atoms or, let's say hydrogen because it's a hydrocarbon we're dealing with. So yes, unsaturated has more than 1 bond, basically, loosely defined. Okay, so basically, it's a hydrocarbon that allows multiple bonds. I'll leave it there. I've said too much. Let's just summarize it. Hydrocarbon allowing multiple bonds. That's better. So 2.2, consider the unsaturated hydrocarbon in the table. Do we have one? And I'm sure most of you are going, yeah, definitely B is our unsaturated hydrocarbon. Okay, because we see we have a double bond there. My goodness, I think my laptop is tired. It's just, malfunctioning a little bit there. Okay, so yes, just wanted to put there. B is our unsaturated hydrocarbon. Now 2,2,1, it says write down the letter. Oh, I'm answering ahead. Write down the letter of this compound. B. Okay. Let me just remove it there. And then 2.2.2, the compound is passed through bromine water in a test tube. Okay, so if you've done experiments in class, you'll know that bromine water is like brown. I wonder if they named it bromine because it's closely related to brown. I don't know. But yes, so you have this compound, this alkene passing through bromine water. Okay, so if you have a multiple bond and there you have your halogen, this is like an addition reaction. Okay, probably it's gonna form a haloalkane. All right, so this is all done at room temperature. Now state an observable change in the test tube. So you have bromine water. Then you're adding this alkene to it. What did we call this alkene? 2,4 dimethyl hex 1E. So you add that alkene to the bromine water, and what do we observe? What change do we observe? So basically, this is really through experiments, something that you would have probably done in class or watched in a video. But basically, the contents in the test tube go from brown to clear. Okay, yeah, it does that. I almost said, well, it's Sunday, I'm from church. So when I think of that, I think the blood of Jesus coming and cleansing us, making us pure and white as snow. So yeah, that's what the hydrocarbon does. This unsaturated hydrocarbon does to the bromine. Okay, but anyway, we have 2.3. You cannot say it's write down 2.3.1, the IUPAC name of compound B. So this is where now you go back to what you had done before and you copy and paste. Okay, so it's notes that you have made on your question paper. So 2,4 dimethyl hex 1E. Okay, 2,3,2. The structural formula of compound E, pentanol, again, you go back to the stuff that you wrote, and you know we have 5 carbon atoms, and at the end, we have your hydrogen atom there. Ooh, it is so exhausting having to put these hydrogen atoms, but yeah, make sure that around your carbon you have 4 bonds, not more, not less, unless if you have a double bond or triple bond, but still you'd have 4 lines around your carbon. And then 2,3,3, the name of the functional group of compound E. Okay, so yeah, compound E belongs to the aldehydes, right? Pentanol, meaning basically it is your aldehyde, but yeah, I've gotten this wrong a couple of times. So you have functional group, right? And you have homologous series. So, oh, how do some people pronounce it? Not homologous, homologous. So the homologous series is your aldehyde, but the functional group, it is your formyl group. Okay. So yes, let's not twist or confuse the two. And 2,3,4, the homologous series, that is a functional isomer of compound D. Propanoic acid and esters are functional isomers. Okay, so we can just go there straight and say it would be an ester. All right, because they ask for the homologous series. They didn't ask for the name of this functional isomer. And now we get to 2.4. These questions can be quite lengthy, but you can really score your marks, guys, with the from question 2 to question 4, your organic compound questions. Please try to score as many marks as you can there. I think it counts about 40% of the paper. Make the most of it. All right, now it says compound A is an alkane. Yes, that's true. Write down the general formula for alkanes. We did write it down, right? CnH2n plus 2. and then 2, 4, 2. The molecular formulae for each of the two products obtained during the complete combustion of compound A. Remember, guys, combustion, the products that come from there would be carbon dioxide and water. Right? So basically, you take your alkane and add oxygen to it, and then your product would be carbon dioxide as well as water. All right, 2.5. Compound C is a primary haloalkane. All right, I told you they're going to tell us something more about compound C. And remember, we just, or I, but basically for compound C, because we didn't know the position of chlorine, we just said it's just chloropropane. Okay, could be 1 chloro, 2 chloro, it could be 1 or 2, but they've told us that it is a primary haloalkane. And for it to be a primary haloalkane, it means that the carbon attached to that chlorine is attached to only one other carbon. So if I put it at the middle, the carbon attached to this chlorine is also attached to another carbon and another carbon. So that's not primary anymore. It is more secondary. Okay, so now we know more information. It is a primary haloalkane. So the chlorine is on number 1. So if you're looking from the left to the right, this is your number 1. If you're looking from the right to the left, this is your number 1. But I'm just gonna write from left to right. So I'm gonna put the chlorine there. It is a primary haloalkane. Great. Now what's the question? 2.5.1, define the term primary haloalkane. Primary haloalkane means that the halogen, the carbon that is attached to the halogen, is connected to one other carbon. That is primary. If it was secondary, it would be connected to 2 other carbons. If it was tertiary, it would have been connected to 3 other carbons. So in this case, it's only connected to 1 other carbon. Okay, just to repeat, the carbon that is attached to the halogen, in this case chlorine, is attached to 1 other carbon. Leave it at that. Loose definition. Okay, so 2.5, that was 2.5.1. I'm not going to write that down. And then it says, write down the structural formula and IUPAC name of an isomer of compound C. So if originally 1, 2, 3, you have your chlorine atom there, okay, an isomer of it, still you have your 3 carbons, and you have to make sure that you have your 7 hydrogen atoms, but now your chlorine atom is going to move to the center, because like I said, you can either have 1 chloropropane. You don't even need to say, if it's a chloropropane, it means it's on the first carbon, okay? Or you can have your 2 chloropropane, okay? So your chlorine can either be on the first carbon or on the second carbon. So that is the structural formula, and then the IUPAC name would simply be 2 chloropropane. Okay, so yeah, that's basically that. 2 marks. And then we get to 2.5 this is 2.5.2, 2.5.1, we said it in words. 2.5.3, classify the isomer in question 2.5.2 as chain, positional, or functional. Okay, chain isomers are when you have maybe a straight line, and then the isomer would be a branched, hydrocarbon, whatever it is. So that's not chain. Positional, definitely, because it changed positions. It went from the first carbon to the second carbon, okay? Functional isomer would be, maybe think about, what is so many words going through my mind. Carboxylic acid. So think about carboxylic acid, a functional isomer of it that we did address in the previous 2.3. Functional isomer of carboxylic acid would be an ester. Okay, of an aldehyde, it would be a ketone. So in this case, we have a positional isomer because the chlorine changed positions from the first carbon to the second carbon. And then lastly, 2.6, that, let's see what this has to do with. It says a chemical analysis of compound X shows that it has the following percentage composition. So we have X percent. I almost wrote X factorial, not percent. The X percent of your carbon, and then you have Y percent of your hydrogen, and then you have 12.5% of your oxygen. Now it says use calculations to determine, or a calculation to determine the value of X. So we want to know the percent composition of our carbon. Now going back to our table, we can see that the general formula here is CnH2nO2, and I was telling you guys that where I've seen where we have two oxygen atoms would be your carboxylic acid or your ester. But like I said, with the hydrogen, you always have H2n plus 1. But anyway, they're not asking for the names or anything. They want us to get the percent composition of carbon. So the one that we have at the moment, the percentage, it is for oxygen. So let's start from what we know and work our way back. So if I have 12.5% of oxygen, I will then say the percent of oxygen would be equal to the molar mass of this oxygen. Okay, molar mass of this oxygen. Let me just say over the total molar mass. Okay, multiply that by 100. So the percentage of oxygen, we have 12.5%. The molar mass of oxygen, we know that we have two from this formula. We have two oxygens, so at least we know the amount of oxygen. And the molar mass of oxygen is 16, if you look at your periodic table. Let's go check, just make sure. Turn our heads, so you can see for oxygen we have 16 grams per mole. Okay, so that's all good. All right, so yeah, we have 2 times 16 for oxygen, and then we still don't know how much we have in total. Right, yeah, my pen is very slow today. So 2 times 16. And we're going to multiply that by 100. Okay. Now it looks like 110. Okay, so basically, the molar mass, we have 2 times 16 all over. Actually, because I've already put this in percentage, I'll just say 12.5%. I don't need to multiply by 100. 12.5% is simply 0.125. And if we calculate that, we have 32 divided by 0.125, and it gives us a value of 256 grams per mole. So that is the total molecular mass of the entire compound, including the carbon, including the hydrogen, as well as the oxygen. So now let's go and see. And let's say now for carbon, we have n amount of carbon, right? So n amount, and we know that carbon's molecular formula, not formula, but molar mass is 12. Okay, plus for hydrogen, we know that it's 1. We're going to multiply by 2n. And then for oxygen, we have 2 times the 16, and that would give us 256. So now we have 12n plus 2n plus 32 is equal to 256. So 14n is equal to 256 minus 32. Let's just take out the calculator. So 256 minus 32 is equal to 224. divided by 14, and you get a value of 16. So N is equal to 16. Now, what do we do with that? We want the percent composition of carbon, which is X percent. Okay, so we're gonna go and say X percent, which is for carbon, is equal to the molar mass of your carbon divided by the total molar mass. And the total mass of carbon, remember carbon is 12 times N. So basically 12 times your 16 divided by your total molecular form, no, total molar mass, 256. And we're going to multiply that by 100, right? So basically, going back to our calculator, we have 12 times 16 divided by 256, and that is 0.75. Multiply that by 100, basically it's 75%. Okay, so that's great. You have 75% carbon. Okay, you have 12.5% oxygen, and the remainder, out of interest, they didn't ask us, I just want to know, you can stop the video. So we also have 12.5. Yes, that makes sense. 12.5% of hydrogen as well. Alrighty, and that is it for question 2. Yeah, it took a while, but let's see how question 3 goes. Thank you for tuning in. Hello everyone, and welcome back to MV Tutors. We're still continuing with the chemistry paper and looking at question 3. All right, thank you for subscribing to our channel, liking our videos, commenting. It motivates one to continue recording. So yeah, haloalkanes play an important role in the chemical industry. Haloalkanes can be made from alcohols. All right, remember haloalkane is an alkane that has one of its hydrogen atoms replaced by halogens such as chlorine, bromine, iodine, fluorine. Did I mention fluorine? Probably did. Yeah. So yes, the following tables can be used to compare the boiling points of some haloalkanes. So you can see A has chloromethane, then B is dichloromethane, and then we get to D, which is tetrachloromethane. All right, and then for table 2, we have fluoromethane. So in the first table, we have chlorine as the halogen. And then for compound E, we have fluorine. All right, and then we have methanol. Al should tell you we have an aldehyde. Then methanol, all right, methanol, that's the alcohol. And then methanoic acid, that is your carboxylic acid. So basically from A to E, that is where you have your haloalkanes. So let us now answer the questions that follow. Now, 3.1, so it says use the information given in the tables above to answer question 3.1 to 3.6 below. Define the term boiling point. Okay, so boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. Okay, I'm not gonna write that down. You know these definitions, they normally ask them. So please make sure you study the definitions and you understand and you know. Okay, and then 3.2, write down the formula of 2 haloalkanes that are the most dangerous at 25 degrees Celsius. 25 degrees Celsius is basically at room temperature. And why would those be dangerous? Okay, so what am I looking for? I'm looking for a haloalkane, right? Be it chloro or fluoro. And I'm looking for it being a gas at room temperature. And the reason why I want it to be a gas, sometimes gases you can't see, some of them are very clear, but when you inhale them, it becomes very toxic to your body. If it's in liquid form, it is what it is. You have the option of not touching it if it might hurt you. By touching it might burn you or whatever, if it's quite acidic or very basic. But when it's a gas, it's like a silent killer. So I'm looking for gases, okay? And I see that chloromethane is a gas, at room temperature, as well as fluoromethane. Okay, so they wanted the formula. All right, so chloromethane, that is where you have your carbon with the 3 hydrogens and your chlorine, as well as the carbon with the 3 hydrogens and your fluorine. Okay, that gases at room temperature, meaning dangerous when inhaled. Yeah, when inhaled, because they are gases at room temperature. Okay. All right, now question 3.3. Describe the trend in boiling point illustrated by table 2, and then explain this trend. So with table 2, you can see that, so you have fluoromethane, then methanol, and methanoic acid. So what I'm going to do, I'm just going to draw the structural formula so that we can see what's actually happening here. All right, so this is the first one, fluoromethane, then methanol. Methanol, meaning we have a double bond to oxygen and a bond to hydrogen. Let's actually make that a bit bent. In real life, it would look something like this. All right, and then we have methanol. So basically, we have our bond to OH, and the rest is your hydrogens. And then we have methanoic acid, so basically Cu. Okay, 1, 2, 3, and then 4. All right, so what trend do we see here? We see that as we go in this direction from fluoromethane all the way to methanoic acid, basically the boiling point increases. Okay, so yeah, our boiling point increases in that direction. Okay, and what do we notice here? I notice that I have an OH group over here and also there. So these last two, actually, you can see that we have some hydrogen bonding. Okay, and over here, you have your typical weak London forces. Okay, dipole, dipole. So London forces. Okay. Okay, let's just go back to the question. So it says, describe the trend. We've described the trend. From fluoromethane all the way to methanoic acid, there is an increase in boiling point. Okay, and explain this trend. Why is it the case? So with fluoromethane and methanol, firstly, you have your weak London forces. Okay, and then we can see then from methanol to methanoic acid, you have your strong hydrogen bonding. Okay, and to overcome the forces that we get with hydrogen bonding, we need a lot of energy. Strong hydrogen bonding, which requires a lot of energy to overcome this kind of bonding, and therefore you would get your high boiling points. Okay, so I hope those 3 marks, yeah. Describe the trend. It's increasing. You have your weak London forces, you have your strong hydrogen bonding, you require a lot of energy to overcome that bonding. I think 3 marks would be sufficient. 4, actually. 4 marks. Yes, so basically, as the strength of your intermolecular forces increases, so does your boiling point. Okay, that's the trend. Describe the weak London forces that we have, describe the hydrogen bonding that we have, and also state that with hydrogen bonding, you require a lot of energy to overcome such intermolecular forces. That's where your 4 marks will come from. And then 3.4. Okay, so it says consider table 1. And let's go to table 1. All right, and it says, what is the relationship between the number of chlorine atoms and the boiling point? So I hope you see here, the more chlorine atoms you add, the higher the boiling point. Okay, so the more your chlorine atoms, the higher the boiling point. That is the trend that we see, right? Yeah, with the number of chlorine atoms. And then 3.4.2, explain the difference in boiling point between chloromethane and tetrachloromethane by referring to the intermolecular force and energy. So with your chloromethane, you have your carbon there, you have your chlorine, and there are your hydrogen atoms. But with tetrachloromethane, literally your carbon atom is surrounded by chlorine atoms. So if you look at your periodic table of elements, chlorine has a bigger radius. It is quite big. I forgot the actual size. I don't think here in your periodic table they show the sizes. No, not really. But yeah, no, not really. But your chlorine atom actually is quite big compared to your hydrogen atom. Your hydrogen atom is quite small. So already there, we have that advantage of size, okay? So I think firstly, just talk about the size, ne? Where are we? 3.4.2, 3 marks, okay? So in that case, we would say that tetrachloride, chlorine, tetrachloromethane, okay? So yeah, tetrachloromethane. Okay, now, how should I write it? Let me just refer to, yeah, the formula. So tetrachloromethane has the larger molecular formula or molar mass. Okay, it has a larger molar mass, and as a result, you would have quite large intermolecular forces for it compared to your chloromethane. And with large intermolecular forces, that means that you need higher energy to overcome those large intermolecular forces. So I think that should be sufficient. Describe the size, how big it is. And the bigger it is, it means you have larger intermolecular forces. With larger intermolecular forces, meaning that you have you require a greater amount of energy in order to overcome those large intermolecular forces. Okay, that's 3.4.2. 3.4.3, state 2 factors that should be kept constant in this investigation to make it a fair test. They were saying we were looking at haloalkanes. When we're looking at these haloalkanes, it is very important for you to use one halogen at least. So at least keep the halogen constant, okay? Because I cannot be looking at chlorine, next thing I'm describing iodine, and then fluorine, and then bromine. Like, keep the halogen the same. Okay, and another thing, if you've kept the halogen the same, in this case for table 1, it is just chlorine, keep the amount of carbons the same as well, because it wouldn't help to still have just chlorine, but you're increasing the amount of carbon. So what you've seen here, they've kept one carbon throughout. So methane all the time. So keep the halogen the same. And how do I say this in nice English? Okay, this is not the time for nice English, but basically keep the same amount or maintain the same amount of carbon atoms. Okay. One more word. My thing is jamming on me. Okay. So maintain amount of carbons. So handwriting is terrible these days, guys. We type everything. We don't write anymore. So it's such a schlep to keep writing. I feel like I should just type maintain amount of carbons. All right, so 3.4.3, that is answered. And now we get to 3.5. where we get back to definitions. Please, guys, question 3 has a lot of definitions. Know what boiling point is. They like asking that, even vapor pressure, melting point, probably. But yes, please know those definitions. They will definitely ask them. Okay. So what is vapor pressure? Define the term vapor pressure. That's basically the pressure that is exerted by vapor. If all goes south, vapor pressure, just swap the words around. It is the pressure exerted by a vapor. Okay, but what about that vapor? So that vapor is at equilibrium with its liquid in a closed system. Okay, yeah, swap it around. Pressure exerted by the vapor. What about that vapor? That vapor is in equilibrium with its liquid in a closed system. And we'll end it at that. And now 3.6, we're almost there. Consider the compounds of methanol and methanoic acid. Remember, methanol is just your alcohol. Okay, you have a bond, OH bond. Actually, I like putting the OH this side. I don't know why, but it looks nice today. Okay, so you have your OH bond. That's your methanol. And then you have your carboxylic acid. Okay, that's where am I? 3.6. Yeah, so your carboxylic acid double bond, and then you have your OH, and just one other bond needed, so that you have 4 bonds around your carbon. Okay, so it says, which one of these two compounds will have a low vapor pressure? Okay, vapor pressure and boiling points are inversely proportional. So the higher your boiling point, the lower your vapor pressure. That's one thing, or one relationship you should really take note of. So now, which one will have the lower vapor pressure? It's the one that has the higher boiling point, and we see that it is methanoic acid. So yeah, therefore 3.6.1, the one compound that has the low vapor pressure is methanoic acid. I've just written the formula actually. Methanoic acid. Okay, now it says explain the answer to question 3.6.1. Why does it have a low vapor pressure? Especially looking at the definition that we gave. Yeah, about what vapor pressure is. Yes, so basically methanol, both methanol, remember when we illustrated there that both methanol and methanoic acid actually have hydrogen bonding between them. Okay, so that's one thing you should start by saying, that they have hydrogen bonds, but in this case, methanoic acid has 2 sides compared to methanol's 1 side for hydrogen bond. 3.6.2. Explain the answer to question 3.6.1. Okay? Remember what we said in 3.6.1? We said that methanoic acid has a lower vapor pressure because the higher your boiling point, the lower your vapor pressure. Okay? And as we had said before, that vapor pressure is actually the pressure exerted by vapor, okay, when that vapor is at equilibrium with its liquid in a closed system. Okay, so now, why is it that methanoic acid will have a lower vapor pressure? Okay, let's go back to both of them. So we can see that both the alcohol and the methanoic acid, they have hydrogen bonding, okay, which is quite strong, okay, where there's high intermolecular forces. But what sets them apart, basically? Why is the carboxylic acid stronger than the alcohol? That is because for the alcohol, there's like, if it makes sense, it has 1 site, okay, compared to your carboxylic acid where there are 2 sites. Okay, so it makes it more stronger. So hydrogen bonding for both, but your methanoic acid, let me just get, yeah, but your methanoic acid, CH2O2, it has, while both of them have hydrogen bonding, methanoic acid has two sides compared to your alcohol. Okay, and because of those two sides, it means that it will have a higher intermolecular forces. And with high intermolecular forces, you require more energy to break them. That is why you then have a higher boiling point. And when you have a higher boiling point, it means then that your vapor pressure, boiling point, therefore, your vapor pressure will be very low. Okay, and I think that is where we end 3.6. Next would be question 4. Hello everyone, and welcome back to NV Tutors. We're still continuing with chemistry, finalizing organic chemistry to be specific, and let us get to it. So it says a group of grade 12 learners is in a school lab preparing an organic compound with a distinct smell of pineapple. Smells good. Something tells me we're dealing with an ester here. They used ethanol and propanoic acid. Okay, F meaning 2 carbons of alcohol. Propanoic acid, it's your carboxylic acid, and you know that when we have when we have an alcohol and carboxylic acid, you do get an ester. Okay, and so they said the balanced chemical equation for this reaction is that another product would be water. So 4.1.1, it says what type of reaction takes place? If an ester forms, then we name it esterification. That is the type of reaction. Some would say condensation, but because an ester forms, for me it makes sense to just say esterification, but condensation is also fine. 4.1.2 says, name one precaution that needs to be taken when heating the alcohol. Okay, so when you heat an alcohol, I think you've seen somewhere there's signs where it says highly flammable or flammable. So alcohol is flammable. You don't want to be heating it in an open flame, or you want it to be contained and doesn't actually, get in contact with the flame, or else you'll see flames. So just make sure that you keep it as far away from fire, or else it's just going to exacerbate it and make it bigger and dangerous, blows up in your face type vibes. So yeah. And then 4.1.3, write down the IUPAC name of the organic compound that is formed. So whenever especially if I draw a structural formula of the formation of an ester, I start first with the alcohol, okay, and then come to the carboxylic acid. All right, and then whatever forms, obviously it will be your ester plus water. So with the alcohol, in this case we have ethanol, okay, so then it will be ethyl, all right, and then ethyl, and then we get to the carboxylic acid. In this case it's propanoic acid, so ethyl propanoate. All right, and that would be the name of your ester. Start with the alcohol, end it off with your carboxylic acid, ethyl propanoate, and that is 2 marks. Then we get to 4.1.4. When 50 grams of impure ethanol fully react with excess propanoic acid, it produces 68.88 grams of your ester. Okay, so calculate the percentage purity of the ethanol. So percentage purity, what is the formula? Percentage purity of your ethanol. In this case, we've been given masses. So I would say then this would be the mass of the ethanol that you actually calculate. Okay, So in this case, it would be the mass of your actual divided by the mass of your theoretical. Okay, what is already there. And you multiply by 100. And so far, we know that we have 50 grams of the impure alcohol. Okay, so we'll be using 50 grams in the denominator. This is what we're looking for. And then we're going to multiply by 100. So let's go and get the actual mass of the ethanol. And for us to do that, they've given us 68,88 grams of our ester. Okay, so we see here we have C5H10O2. Okay, so if we want the number of moles of the ester, we're going to need to get the mass over the molar mass. And what is the molar mass? The molar mass is 5 times the carbon, which is 12 grams per mole, plus 10 times the hydrogen, 10 times 1, plus 2 times the 16. Okay, so we have 60 plus 10 plus 32, and that would be 102 grams per mole. All right, so that's the molar mass. So now the number of moles for the ester is your mass, which is 68,88 divided by 102 grams per mole. So then we have 68,88 divided by 102, and that gives us, I think, just round off to 3 decimal places just to be safe for now, or even better, just save your answer. Okay, so we have that amount of mole for the ester. I'm not gonna write down the full formula but we're not interested in the ester, we're interested in the alcohol, which is ethanol. And looking at our formula here, we have 1 mole of the ester, and we also have 1 mole of the ethanol. So it's a 1-to-1 ratio. Okay, so therefore the number of moles for the alcohol, for ethanol, it's actually going to be the same. It's going to be 0.675 mole. Now that we have the number of mole, if we want to get the mass, remember number of mole is mass over molar mass. So mass is number of mole times the molar mass. Now what is the molar mass for the ethanol? We can look at our formula here, molecular formula. So we have 2 times the carbon plus 6 times the hydrogen plus oxygen, which is 16. Okay, so we have 24 plus 6, which is 30. 30 plus 16, what am I writing? 30 plus 16 is equal to, what do I do now? It's equal to 46. Okay. So we have 46 grams per mole. And then to get the actual mass, we take 0.675 multiplied by 46, and that gives us 31.06 grams for our alcohol. And now we can go back to our formula where we said that the percent purity is the actual mass, right, divided by the theoretical. So our actual mass is 31.06 divided by 50 multiplied by 100. And that gives us a value, percent purity, of 62.13%. Yeah. And that's it. That's the percent purity. If you don't like the word theoretical, I would say, okay, it's the actual that we calculated divided by the impure mass. Yeah. And now we get to 4.2. 4.2. Prop 1-ene is an unsaturated hydrocarbon, and compound X a saturated hydrocarbon. So if it is saturated, it means we have an alkane. So they react with chlorine as represented by the incomplete equations. Okay, so prop 1 in, just going to say 4.2, prop meaning we have 3 carbons. First, so on the first carbon we have our double bond. Okay, and then there we go. And it reacts with Cl2. Okay, that's reaction number 1. Reaction number 2, we have X plus chlorine, and it gives us 2-chlorobutane. So we have 4 carbon atoms on the second one. That's where we have the chlorine, and the rest are your hydrogen atoms. And we have Y, which I would guess would be the other chlorine, because we have 2 of them, right? So this probably is that, and that is probably butane. Okay, now let's answer the questions. So what type of reaction, elimination, addition, or substitution, takes place in reaction 1 and reaction 2? Okay, so in reaction 1, we have an alkene. It's a double bond, all right? So this double bond will break into single bonds. So if previously we had 1, 2, 3, 4, 5, 6 hydrogens, now you're going to still have the 6 hydrogens, but you're going to add on these chlorine atoms. So you basically have addition for the first one. Remember, if it is not saturated, you can still add onto it. But if it is saturated, like we have here for reaction 2, then something must happen. You're going to basically substitute, okay? If it went from an alkane to an alkene, then you eliminate it. But in this case, it was just pure substitution. All right, now 4.2.2, write down the structural formula and name of the product formed in reaction 1. So in reaction 1, we had prop 1 in, that's your alkene. So basically you're going to form a haloalkane. So what do we name that one? So name, or write down the structural formula. Okay, we already did, kinda, but let's do it. Okay, so we have 3 carbons. Right? And you have your hydrogen atoms over there, 6 of them. And on your first and second carbon, whether you take the first as the left or the right, doesn't really matter. So this is the structural formula. So basically you have 1,2 dichloro, 3, it is dichloro-propane, because now it is a haloalkane. It's not an alkene anymore. All right, and then 4.2.3, list the reaction condition necessary for reaction 2 to take place. Reaction 2 is where you have your alkane, and you're going to be doing some substitution to get a haloalkane. At the end, you're going to have a haloalkane. So for substitution to take place, you need some energy, you need heat. Okay, heat or light, but yeah, need some heat so that things can happen. So 4.2.4, write down the IUPAC name for reactant X. So reactant, remember we did say that we are thinking it could be butane, because butane plus chlorine does give you chlorine on the second carbon, so 2-chlorobutane plus HCl. So I would say that X is butane. And 4.2.5, write down the name or formula of product Y. So product Y, we did say that, yeah. So if you have your 2-chlorobutane, what remains, there should be a hydrogen that has been taken out, replaced by the chlorine and an extra chlorine, so it's HCl. When I see HCl, I immediately want to say hydrochloric acid, but let's refrain from using acids at this point. Let's just say hydrogen chloride. Okay. I don't know if they accept. Actually, it's actually safer to use the formula. So hydrogen chloride, but I would suggest that you use the formula just to be on the safe side. And that's it for 4.2. All right, now 4.3, we're almost done. Now consider the organic compound of 2-chlorobutane. Just a reminder, the chlorine is on the second carbon, and we have 4 carbons. Okay. This compound can either undergo elimination or substitution reactions in the presence of a strong base, such as sodium hydroxide. Okay, it is a strong base. If it has a hydroxide to it, it's quite strong. Now, 4.3.1, which reaction will preferably take place when 2-chlorobutane is heated in the presence of concentrated sodium hydroxide and ethanol? Sorry. So basically, we have our haloalkane, okay, and it is heated in the presence of, so there's a difference between when you have concentrated sodium hydroxide versus diluted sodium hydroxide, okay, and that really is important for you to understand. And for those of you who don't get the theory, I suggest you Google Mind the Gap, which summarizes all these reactions quite nicely, if maybe your textbook is not that, doesn't explain that well. Okay, so if you have a haloalkane, all right, these are the reactions that are undergone by haloalkanes. Okay, you have substitution and elimination. But if you have a haloalkane and we have a concentrated solution like sodium hydroxide or potassium hydroxide, okay, then yeah, we undergo elimination if it's concentrated. But if it's dilute sodium hydroxide, then we're looking at substitution. So concentrated sodium hydroxide, elimination. Diluted would be substitution. So let's get back to the question. So it says, which reaction will preferably take place when we have concentrated sodium hydroxide? It would be elimination. Okay, elimination. And if we are eliminating, okay, but let me not get fast, just 1 mark. Let's just read the next question. So it says, write down the IUPAC name of the major organic compound formed in question 4.3.1. If you want to know about major and minor products or compounds formed, please, you either apply Zayatev's rule or Markovnikov. Go read about it, okay? We still have some time. So the IUPAC name for the major compound formed in 4.3.1. Remember, since we're dealing with elimination, it's over here. So if you are eliminating, you're going to get a double, double bond, okay? So you're going to get an alkene, is what I'm trying to get to. So, haloalkane plus concentrated sodium hydroxide, what will you get? You are eliminating your chlorine over here, okay? And they wanted just the name. They don't want the structural formula. But yeah, let's just see what will happen then. What will the name be? If you're going to eliminate your chlorine over there, okay, you're going to get, like we said, you're expecting to have an alkene in this case, right? And if you're going to get an alkene, then you have your 4 carbons. They didn't ask for the structural formula, it's okay. That is really just for demonstration purposes. So you're going to get butene, but something in. And that's why they're saying the major product that you're going to get. So where, if you eliminate the chlorine, will your product be? Is it going to be on the second carbon or the first carbon? Well, in this case, it's going to be on your second carbon. Okay, we'll go read about it. So you'll get but2ene. Okay, and then 4.3.3, use structural formulae to write down a balanced equation for the reaction that takes place when 2-chlorobutane reacts with a dilute sodium hydroxide solution. So I did briefly say if it's dilute, then it's going to be a substitution reaction. So let's just write down the structural formula. Okay, we had the chlorine on the second carbon, 2-chlorobutane. And we have sodium hydroxide. This time it is dilute. Okay, so if it's dilute, we're looking at substitution over here, not elimination. Okay, so now what do we get? But they wanted structural formulae. Okay, so if it's structural, I'm not going to use sodium hydroxide like that. I need to put in labels. So sodium, okay, hydroxide. So we have our hydrogens over there. Okay, need to make sure. Okay, we have our sodium hydroxide. It is diluted. Yes, it's diluted here. So we're gonna get our substitution reaction. What happened to the 2 here? But2ene. Okay, and then what product are we expecting? Because we're going to deal with substitution, what are you substituting and what is your product? Okay, so in this case, I know I'm not going to have sodium in that organic compound, but there's OH there. Okay, again, if you missed it, here it is. If you have substitution, so diluted sodium hydroxide, you will get an ethanol, alcohol, and sodium chloride. So in this case, yes. Substitution, you take out the chlorine, and you're going to put in your OH group. All right. So on your second carbon, you're going to get your OH group. Please don't put the OH together. They need to see the structure. So we need to put in the lines in between the bonds to indicate the bonds. Okay. So there it is. And you have your hydrogens there. Oh, it can be such a nuisance having to put in all these hydrogens. Okay. Plus what's left behind is your sodium and your chlorine. The sodium chloride. Even that one, I need to put the bonds in between. So yeah, I didn't calculate my working space over there. Let me just do this. So just on top, we have sodium chloride. Oh, 4 marks. Okay. Okay, so that's cool. And then 4.3.41 mark. It says write down the name of the type of substitution reaction that takes place in question 4.3.3. In this case, it would say it is hydrolysis. Okay, yeah, we are kind of hydrating it. But yeah, and that is it for question 4. We're done with organic chemistry. Question 5 next time. Hello everyone and welcome back to MV Tutors. I'm Tilo and I'll be looking at question 5 with you from the chemistry paper written in June. I hope this will help you prepare for your chemistry prelim. All right, please don't forget to like our videos as well as subscribe to our channel. I will not be showing my face at the moment because I just woke up and I thought, let me just record and not delay any longer, so that you guys can study. Today, you guys are writing your prelim, physics prelim. So when you come back, just rest a bit and then get back into chemistry mode. You're almost there. And this is specifically for the Gauteng province. I don't know what other province is writing chemistry on Tuesday. But yeah, let's see how far we can get. So, a group of learners uses the reaction of magnesium ribbon, okay, with dilute hydrochloric acid to investigate factors that influence the reaction rate. The balanced equation for the reaction is, so we have magnesium in solid form, and then you have the hydrochloric acid. You're going to get a salt, magnesium chloride, as well as hydrogen gas. And we can see that our enthalpy there is less than 0. Okay, that should indicate something to you. Now, the hydrogen gas produced in the reaction rate was collected as shown in the diagram. There is a video where I address the rates of reactions. Okay, let's see if we can have a look at that quickly. So if you go to our YouTube channel and you go to playlists and you browse over through the chemistry lessons, where is it? The rate of reaction measuring. So that particular video, it addresses these adverts. It basically addresses all the methods that you might expect. So you can go there and just have a look. Let me see, do I have timestamps for this one? No, I do not. But let's just wait a little bit. Sorry for these ads. But yeah, so basically this is where I summarize and you can get a summary of it and understand it much better. Okay, now we are watching adverts. You can definitely fast forward if you can, if an advert is not playing on your side. So you can see the different methods that I do have a look at. Okay. Yeah. So if you're measuring turbidity for one, if you want to get the volume of a gas product with the syringe, okay. So yeah, and then you have a look at the graphs and the tables. So yes, at your own time, you can go through all of this so that you can get a better understanding of the different types of way we measure the rate of reaction. Okay, now getting back to the question. By the way, how does the magnesium ribbon look? It looks something like this. All right, so yeah. Anyway, 5.1, is the above reaction exothermic or endothermic? Now, what gives that off? Your enthalpy. If your enthalpy is less than 0, that means that it is exothermic. All right. And what reason would you give? Well, yeah, it is exothermic because your enthalpy or the heat of reaction is less than 0. That's basically that. And then 5.2, guys, this is a section where you should really score marks. Rate of reactions, not that bad, not that tricky, like your acids and bases and Le Chatelier's principle and all of that. So please score as many marks as you can. 5.2, it says, describe the method used to collect the hydrogen gas. Okay, so what happens? You have your hydrochloric acid in here and you have your magnesium ribbon. Then the reaction occurs, your hydrogen will come through this tube over here. I almost said a straw. This tube over here, all right? And in this beaker, you have water. So where is a gas most likely to be? You won't find the gas sitting comfortably at the bottom. It wants to go up, right? It is less dense, so it will go up. So as the gas passes through the tube, it now goes into the syringe. So as the gas goes up, it pushes the water down. Gases are quite strong, don't underestimate them. So now your gas will be there trapped in the air there. And you'll see as your water reduces the level, you can read off then how much gas has already been captured there. So that's how you know the amount of the gas. Now for 1 mark, describe the method used to collect the hydrogen gas. Well, I would say when you have a downward displacement, I said a whole lot of things. You can write that down. Now I'm saying download. Ooh-wee. Yeah. But to summarize everything, I would say the downward displacement of water. If you don't remember this, describe what is happening. Okay? Downward displacement of water. That's a simplified version for 1 mark. If it was 3 marks, I was going to explain everything, but the gas pushes the water down in the cylinder and moves up into the cylinder, and it passes, yeah, exactly what I said before. All right, now 5.3. In one of the experiments, 5 grams of magnesium ribbon was added to the hydrochloric acid solution. Okay, now if the average rate or reaction rate is 7.5 times 10 to the negative 4 moles per second, calculate the volume in cubic centimeters of dilute hydrochloric acid used up in 1 minute if the solution has a concentration of 1.5 mole per cubic decimeters. And it is 5 marks. Okay, a lot of information has been given. So let us summarize what we know. We know that the mass, I'm just going to say mass of magnesium is 5 grams. We know that the average rate of reaction, I'm just going to say RR. The unit there is mole per second. So we have change in number of moles, change in time, and that is 7.5 times 10 to the power negative 4, okay, mole per second. And then the time that has been given, delta T, is 1 minute. We normally use seconds. So we have 60 seconds, and what else has been given? The concentration, so C, which is equal to N over V. Try to write down your formulas as well as you write this down. Like the mass for 1, well, here you'd say number of moles is your mass over your molar mass. Okay, just to remind yourself. So the concentration is 1.5 mole per cubic decimeters. All right, so this is all the information that you have, and what they want is the volume, okay, in cubic centimeters. So what is the volume? All right, so I can already see that I'm going to use this formula to calculate the volume. I have concentration. Can I get the number of moles? Because in this formula, I have the reaction rate, I have the time, I can get the number of mole. And even in this equation, I have the mass, I have the molar mass, I can get the number of mole. So what's recurring here is I need the number of mole. So let us start then. All right, so if we use our formula, N, number of mole is equal to your mass over your molar mass. The mass has been given. We're looking at magnesium at this point in time, okay? So the mass is 5 grams. And the molar mass, let's just have a look at the periodic table. Just bear with me. Twist your head. Okay, on the second group, you can see third row, group 2, magnesium is there. It has a molar mass of 24 grams per mole. All right, let's get back to our question over there. All right, and if we get the number of mole there, and this is the initial number of mole, okay, before the reaction occurred. So we have 5 divided by 24, and we get 0.2083. Just store that number for yourself. So this is the initial number of mole for magnesium. All right, then they tell us about the average reaction rate. Okay, so we're done using this formula. Now we're going to go to the reaction rate. Okay, of magnesium, which is the same as the reaction rate for the hydrochloric acid, but we have more information for magnesium, so we're going with that. And we know that it is the change in number of moles over the change in time. Okay, our reaction rate. So in this case, because the reactants are getting less, so during a reaction, your reactants decrease and the product increases. And because we're looking at the reactants at the moment, we don't have the product yet, we're gonna have 7,5 times 10 to the power negative 4 mole per second, but it will be negative, okay? Because, like we said, the reactants are decreasing. Now, in terms of the number of mole, basically we have the final number of mole minus the initial. What we calculated previously is the initial number of mole and divided by the time. So the time there is 60 seconds. Okay. Don't really need to put the unit. We will be consistent. Okay. So now we're gonna calculate now the final number of mole after the reaction has occurred. So the final number of mole would be the negative 7,5 times 10 to the negative 4 multiplied by the 60 seconds, if I take it that side. And then I'm going to add the initial number of mole. Okay, so I'm also taking it that side. And if I add it, it will be 0,2083 blah blah blah. That's why I shouldn't remove it from the calculator as yet. So let us calculate. We have negative 7,5 times 10 to the negative 4 multiplied by 60 plus the answer that we got previously. Oh, I didn't put the negative. So the negative 7,5 times 10 to the negative 4 times 60 plus 0, now my thing has okay, let's just go back there. Yeah, my answer has changed now. So this is my answer. Let's start again. Sorry, it's negative 7,5 times 10 to the negative 4 multiplied by 60 plus the answer we got previously. And then we have 0,166 mole. If you want to save the answer, you can just say shift, store, and put it at A so that whatever happens, we always have the answer. So now we have the number of moles, okay, after the reaction, the final number of mole for magnesium, okay? Okay, now what do we do with that? Okay, so looking at our equation there, for every 1 mole of magnesium, okay, we have 2 mole of, let's write it down. So every mole, 1 mole of magnesium, we have 2 moles of hydrochloric acid, okay? And then, so now we have our initial and we have our final. So if we want to get the amount of moles that were used up, because that is what they're asking here, if the average reaction rate is that, calculate the volume of dilute hydrochloric used up, okay? Not the dilute hydrochloric initially or finally used up. So if I'm going to get the number of moles that were used up, it would be the initial amount of moles that I had, and then I'm going to subtract the final, okay, and then we're going to see the amount that was used up. All right, so let me see what is A over here. It's the 166. Okay, so now let us see the initial, which was the 5 over 24. I didn't save that answer after telling you guys to save. And then minus the final. Okay, so the used up number of mole is 0,044. 2. All right, and now what we're going to do, so if I have 0,042 for magnesium, I'm going to have twice for hydrochloric acid. So it is 0,084 for hydrochloric acid. So now we have the number of moles used up for hydrochloric acid. Okay. Now I can determine the volume. We can go to our last equation. Remember, concentration is number of mole divided by volume. So now concentration, okay, number of mole over volume. So volume is number of mole over concentration. And this is number of mole now for hydrochloric acid, the used up hydrochloric acid, which is 0,084 divided by your concentration, which is 1,5, and we get an answer of 0,056. But this is cubic decimeters. We still need to take it to cubic centimeters. Okay, and in order for us to do that, we're going to multiply by 1,000. All right, so we get 56 cubic centimeters of used up hydrochloric acid. And that's it. That's your 5 marks. Okay, so really what's important with these kinds of questions is to understand what is happening. The information that you have, make sure you summarize it so that you know what you have to do. All right, now let's move forward. Now we have the concentration of the acid used as a function of time in this experiment is shown in the graph below, and the graph is not drawn to scale. So we can see, do you see that the concentration initially will decrease? The reactants, concentration of reactants decreases, right? While that of the products will increase. Okay, so the acid used will decrease. Even if you were to use magnesium, it would decrease as well. Okay, now 5.3.2, it says, how does the rate of the reaction change between T1 and T2? Okay, now be careful, guys. When you're talking about the rate, please don't look at the graph and think, oh, because it's going down, then the rate is decreasing. No, rate has to do with how quickly something occurs. So what you're going to look at is the steepness of the graph. Okay, so you can see it's here, it's starting out, and then it's not flat per se, but as you go, it gets very steep. So between T1 and T2, it is very steep. And because it's very steep, the gradient is quite high. Okay, because it's very steep, you can then conclude that the reaction rate is actually quite high. It is increasing. Okay, so the rate of the reaction is increasing. Okay, so you're going to write down increases. All right. And then they're going to ask probably why we say that. And we need to make use of the collision theory. So with the collision theory, this is what, 3 marks. So you need to state at least 3 things. All right. So remember, initially we said that this type of reaction is exothermic. Okay. And when you have an exothermic reaction, remember, exothermic reactions release heat. Okay. So therefore, your temperature will increase. Now, the nice thing about an increase in temperature means that the kinetic energy increases as well. Okay, so when you have energy, when you have heat, kinetic energy as well will increase. Okay, so the kinetic energy increases, kinetic energy of the particles will increase. All right, and when the kinetic energy of the particles increase, you'll have particles that have enough energy to move. Okay, particles will have enough energy all right, to start moving, okay? And when they move, they will collide. And the more they move, because there's an increase in kinetic energy, because of the increase in temperature, then you'll have more effective collisions. If they don't move much, they won't collide much, so you won't get much of effective collisions. Okay, so particles will have enough energy um, to move or to collide. Okay, and if that's the case, you will eventually get more effective collisions. Is it 1L or 2Ls? One, 2Ls, 1S. Yeah. So have more effective collisions that are taking place per unit time. Okay. So yeah, quite important. Now 5.3.4. Explain the shape of the graph and what happened after T3. So you can see after T3, it's quite flat. What does that tell you? The reaction has ended. Your reactants are probably used up. So yeah, and you can see, so basically the concentration has remained the same, right? So it means your reaction is completed. Yeah, I think they will accept it if you just say the concentration remains the same. All right. And when does it normally stop? When does your reaction come to a standstill? If your limiting reactant has been used up, you can't have, there's nothing more. It's used up, that's it. Okay, so yes, but ultimately the reaction is completed. Now we get to 5.4. Question 5 was rather long. So now we have the Maxwell-Boltzmann distribution graph obtained at low temperature. So number of molecules versus the molecular or kinetic energy. Again, there is a lesson that I did on the Maxwell-Boltzmann graph. So you go to the playlist where we have chemistry lessons and we have it there, Maxwell-Boltzmann graph. Okay. Obviously, there'll be adverts, but yeah. Anyway, so it says here number of moles versus the kinetic energy, and the EA here is your activation energy. So now it says copy the graph given above in your answer book and use a dotted line and indicate on the graph how this distribution will change at a higher temperature. So let's just indicate it over there. This is what we're getting initially, and you have your activation energy right here. Now, I address this in the lesson, okay? And if you want to look at, so I look at the different effects. If you have an increase in temperature, if you increase the concentration, if there's a catalyst, and. So let's just go to the one where it talks about temperature. What happens? Okay, so in this case, the graph here on the left would represent an increase in temperature, and the one on the right will represent a decrease in temperature. So I hope you can see that. This is an increase in temperature. My face is in the way. Yes, this is an increase in temperature, and that's a decrease in temperature. Okay, now let's go back to the question. All right, so it says use a dotted line to show what would happen when you have a higher temperature. So when you have a higher temperature, do you see that there are a lot of particles here when you have a lower temperature? It means these particles have not received sufficient energy to overcome the activation energy and start forming reactions on this side. Okay, but now when you increase the temperature, the number of particles here will decrease. All right, so I'm going to use a dotted line. So number of particles will decrease over here, and you have, it'll look something like this. Okay, your activation energy will still remain where it is. Okay, so getting back to our graph over there, you can see activation energy still the same, but number of particles over here, they're still the same. You still have the same amount of number of particles, but now your most probable energy actually shifts to the right. I hope you can see that. Okay, so yeah, that is basically that. That's how you would draw that graph. And then now 5.4.2, that's the last question. It says a catalyst was added to the reaction. Refer to the graph to explain fully how the catalyst affects the rate of reaction. Now, we know that a catalyst, it speeds up the rate of reaction. I hope you know that. So in this case, your activation energy, if it was probably what, 600 joules, if you add a catalyst, your rate of reaction, your activation energy will move to the left actually, because you don't need this high activation energy anymore. You just need a lower one. Okay, maybe around 400 joules. And I also do address this as well in the lesson, I think somewhere around, yeah. So the effect of adding a catalyst, how would that look? Okay, let's see. Yeah, so you'll see if you add a catalyst, your activation energy becomes less, which is what we are expecting in any case. All right, so yeah, now if we answer that, what would we say? And this is for 3 marks, so you can't just say activation energy lowers only, you need to talk more. But we see that the activation energy actually moves to the left. All right, or you could say that it becomes lower. And then if that's the case, it means that you'll have a lot of particles, more particles than will have sufficient energy. Okay, sufficient energy. And we like it like that, because if they have sufficient energy, it means that you'll have more effective collisions that are taking place. Okay, and it's important to say the effective collisions that take place that happen per unit time. So more effective collisions per unit time. All right, and I think that is it for question 5. See you guys in question 6. Hello everyone and welcome back to MV Tutors. I'm Tilo and I'll be going through question 6 with you. We're still on the June exam and I hope this will help you prepare for your prelims. So it says, during the industrial preparation of ammonia, nitrogen gas and hydrogen gas react in a closed container until the following equilibrium is established at a constant temperature of 472 degrees Celsius. So you see there's our nitrogen gas, hydrogen gas, and we get ammonia gas, and we see that our enthalpy is less than 0, so we have an exothermic reaction. Now 6.1 says, state Le Chatelier's principle. The whole thing about Le Chatelier is you're at peace. Something came and disturbed that peace, and you're trying to establish another peace by opposing that thing that disturbed your peace. Okay, but instead of peace, we're going to talk about equilibrium. All right, so let us state Le Chatelier's principle. It is basically when equilibrium in a closed system. Guys, closed system is very important. If you have an open system, Le Chatelier does not apply anymore. So it has to be a closed system. So when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. That's basically that. And 6.2 says, after equilibrium has been established, the temperature remains constant. Explain this observation. Okay, so now that we have equilibrium established, if you had any changes in your graphs, whatever, this is where it becomes constant. Okay, So what does that tell you? It means that, okay, my eraser does not want to work anymore. All right, there you go. So what has happened? So when equilibrium is reached, the rate of the forward reaction is basically equal to the rate of the reverse reaction. Okay, or we could say that so the rate of your exothermic reaction is the same as the rate of your endothermic reaction. So your temperature will neither increase nor decrease. It will just remain the same. You're going to write all of that down. Then 6.3, a catalyst is now added. How will this affect the equilibrium? Ladies and gents, the catalyst affects the rate of reaction. It doesn't affect equilibrium at all. Okay, so to summarize, we are not expecting any effect. Okay, so yeah, no effect. Okay, 6.4, the temperature is increased to 672 degrees Celsius. Okay, so it increased by 200 degrees Celsius, all right? Now it says, use Le Chatelier's principle to explain what will happen to the concentration of ammonia. Now, as you can see, ammonia is the product, all right? So, whenever you have an increase in temperature, that deals with your endothermic reaction, okay? So an increase in temperature favors the endothermic reaction. And in this case, we have the forward reaction is exothermic, okay? Now it means your endothermic reaction is actually the reverse reaction. So will it be in favor of producing ammonia or more of your gases, your nitrogen and hydrogen? Well, in this case, it will produce more nitrogen and hydrogen. Therefore, what happens to the concentration of ammonia? The concentration of ammonia will decrease. And now moving along swiftly, this question is going rather quickly. The equilibrium constant for this reaction is 4,96 at the original temperature of 472 degrees Celsius. The volume of the container is 0,5 cubic decimeters. The equilibrium concentrations are as follows for ammonia, that, and hydrogen, we have that respectively. Now calculate the concentration of nitrogen gas at equilibrium. Now remember our Kc formula is the concentration of the products. So we have ammonia, and the number of mole becomes the exponent. So we divide by the reactants. So we have nitrogen gas. Another thing about using the Kc formula, it is for gases as well as aqueous solutions. If you have solids and liquids, they do not form part. They just will have a value of 1 for equilibrium. Okay. So nitrogen, we only have 1 mole, so it's just to the power 1. We don't really write that. And then we have hydrogen gas, 3 moles of it, so to the power 3. So I'm looking here for the concentration of nitrogen. So I'm going to make nitrogen the subject of my formula. So concentration of nitrogen is there. I'm going to take it that side, and Kc will be divided. So Kc is going to take its place. Okay, I'm just going to do a swapping thing. All right, so now let me just remove those arrows, but I was just showing you what I'm planning on doing so that you're not surprised. So we have the concentration of ammonia. Actually, yeah, it's fine. I've already started. Let me just continue. I could have just substituted the values there. So no, what am I doing now? I should put Kc because N2 and Kc swapped. Okay, so we have Kc, not the concentration of Kc, but just Kc as a value. Okay, and we have the concentration of hydrogen there to the power 3. So what is the value of ammonia? It is 0.28 squared. The Kc value is 4,96, and for hydrogen is 0,16, and that's cubed. So let's put all of that into the calculator. So 0,28 squared divided by 4,96 multiplied by 0,16, and that would be cubed. And you get an answer of 3, let's put this calculator over here. Get an answer of 3,86. And this is concentration, right? So concentration of nitrogen is 3,86 mole per cubic decimeters. All right, we're almost there. Now we're on to the last question. All right, last question, 6.6. Calculate the initial mass of nitrogen that was used. Okay, were we told anything about what happens initially? Not really. All we know is the ratios of nitrogen, hydrogen, as well as ammonia. And what we do know is the equilibrium concentrations. So in this case, I suggest we draw the rise table, see what we need, and then try to fill it in. Okay, so we have nitrogen. Okay, and we have hydrogen gas, and then we have ammonia. Alrighty, so we're using our rise table. So with rise, we start with the ratios first. So nitrogen has 1 mole, hydrogen has 3, and ammonia 2. Like I said, we don't really know anything about the initial. If we did, we would just calculate the initial mass. And all of this, we're going to put it in mole. Okay. Now let's see. We know initially that there is no product at the beginning. So ammonia will be 0. Do we know anything about the change? Not at the moment. But we can get our equilibrium because we already have values for that. So our equilibrium, we know that for nitrogen at equilibrium, so I'm going to start with nitrogen. So concentration is number of mole over volume. Therefore, number of mole is concentration times volume. Now for nitrogen, we calculated it previously. We got 3,86. Okay, that is the concentration, 3,86. And they told us that the volume of the container is 0,5 cubic decimeters. Okay, and then let's just write everything down. So for hydrogen, number of moles there would be 0,16 concentration multiplied by 0,5. And then for ammonia, we have 0,28 multiplied by 0,5. So what are the number of moles at concentration for all these? Okay, so we'll start at the bottom. For ammonia, we have 0,28 times 0,5, which is 0,14 mole. And then 0,16 times 0,5, that is 0,08 mole. And then we have 3,86 multiplied by 0,5. We're basically halving all the values. So we have 1,93, and we can fill those in. These are the mole, okay? So we have 1,93. For hydrogen, we have 0,08. And then we have 0,14. So I think what we can start with, we don't really have information for the initial nitrogen or the initial hydrogen. So for now, we can leave these blank. But because the initial ammonia, initial number of moles for ammonia was 0, we can then say the change then would be 0.14. Okay, because remember for the products, okay, let's indicate it with a double line. For the products, you add, okay, because you're getting more products, but for the concentration, because the concentrations are being depleted, the reactants are being depleted, you're going to have a negative, but the product we're adding. So at least we have the 0.14. Now we can use the ratio. So the ratio of nitrogen to, or rather of ammonia to nitrogen, is a 1:2 ratio. So if you have 0.14, then here you're going to have 0.07. Okay, and then we're going to say we have a value here, minus 0.07 gives us 1.93. Okay, let's just fill up the whole table. I don't think we're going to get marks for hydrogen. That's not what they were asking, but let's just fill it in. And then you can take the 0.07 because the ratio for nitrogen to hydrogen is 1:3. So we can multiply it by 3. So you're going to get 0.21. Okay, and that would be your y. So x, in essence, minus 0.07 is 1.93. Now, what is 1.93 plus 0.07? That gives us 2. So there we have our initial amount of mole, which is 2 for nitrogen. And then for hydrogen, basically that would be y minus 0.21 is equal to 0.08. And that is going to be 0.08 plus 0.21, and that is 0.29. Okay, but what we are really focusing on is the initial amount of moles for nitrogen. Now that we have that, we can definitely calculate the mass for nitrogen. All right, so we know that number of mole is equal to mass over molar mass. So your mass is number of mole multiplied by your molar mass. Number of mole that we have, we calculated it to be 2. Okay, and the molar mass for nitrogen, we're going to have a look at the periodic table. So nitrogen is there. Okay, we have 14. But remember, nitrogen gas, we have 2 nitrogen elements. Okay, not elements, but yeah. We have 2 molecules of nitrogen. So 2 times the 14 will be 28. Okay, and then in essence, if we calculate, let's go back to our question. So we have 2 times 2 times 14, and that gives us 56 grams. Okay, and then we will be done. We're done with our question. So that is 56 grams. That is the initial mass of nitrogen. And we are done with this question. So see you guys. Question 7. Hello everyone, and welcome back to MV Tutors. I'm Tilo, and we are completing this Gauteng June exam finally. Yeah, paper 2. So let's get right to it. This is the section of acids and bases. It is to some or to many a thorn in their flesh, but let's debunk that theory. Okay, it will not be a thorn in your flesh. You will really do good in it. So 7.1 says, define an acid according to the Bronsted-Lowry theory. So you have 2 theories. You have the Bronsted-Lowry theory, and you also have the Arrhenius theory. A lot of people don't really like referring to the Arrhenius theory because of its limitation, where it's only applicable to watery solutions. Okay, but according to the Bronsted-Lowry theory, an acid is a proton donor. All right, and that's it. Proton donor, you get your 2 marks. With the Arrhenius theory, an acid would be one that forms H plus or H3O plus ions in water. Hence, I said the limitation of the Arrhenius theory is that it has to be in water. If it is not, then we have problems. So we don't want to work with things that have limitations. Now it says the table below shows the ionization constants. Okay, so for acids Ka, for bases Kb. So ionization constants of two acids of equal concentrations. So you have sulfuric acid and you also have sulfurous acid. And you can see that sulfuric acid is quite a strong acid. So the Ka value actually tells you how strong or how weak your acid is. Kb tells you how strong or weak your base is. So in this case, sulfuric acid is quite strong because you have a number higher than 1, whereas sulfurous acid is quite weak. It basically means it doesn't dissociate or it doesn't ionize completely. Now 7.2.1, it says which one of these acids will have a higher electric conductivity? Okay, will it be sulfuric acid or sulfurous acid? Sulfurous acid. I would say it will be sulfuric acid because the Ka value is very high. Again, that's the reason for the answer. You have a higher Ka value, which tells us that this strong acid will ionize completely. Okay, so higher Ka value means you have a strong acid, and as such, it will ionize completely. All right, and then we have 7.2.2. Make use of a chemical reaction to show the ionization of sulfuric acid in water. All right, so you have your acid in water. Remember, water can act as a base or as an acid, but if you have this strong acid, I'm just going to assume it's in solution, and then you have a water, which is a liquid. In this case, the water will act as a base. All right, and you can use two arrows like that to show it's a forward reverse reaction. So what would happen then? Remember, we said that an acid is a proton donor, so it will donate one of its H atoms. Because it's in water, you can also use the Arrhenius theory for acids, okay? So it forms H3O ions in water. So we know that one of the products then would be H3O. So if it donates one of its proton, because it keeps donating it as it goes, you'll be left with HSO4 minus, all right, because you donated one proton, so it will be now more negative. And then you have as another product H3O plus. And you just need to make sure that everything balances, okay? So you have 4 hydrogen atoms over here, 4, 1 sulfur, 5 oxygen, yes. Okay. Another way that you could have looked at it in order to show its complete ionization, you would have started off with your sulfuric acid. My 4 looks like a plus. And it's in water, right? So for it to dissociate completely, guys, by the way, this is the answer, okay? You get your 3 marks. You don't have to go to this next step, but I'm saying if you did write this instead of the first one, that is also it's also good. So if you show complete dissociation, meaning you donate both H plus ions, you would be left with a naked SO4 where you have SO4 2 minus, and then you have 2 of the hydronium ions. Okay, so that's another variation, but you need to then check. You have 6 H atoms over here, and this side you only have 4. So I think let's just put a 2 there. So you have 4 plus 2, that's 6. 1 sulfur, yes. 5, 6 oxygens, 2. Okay, everything is balanced. So yeah, that also gets you to have your 3 marks. Or was it 2 marks? 3 marks, yes. Okay, now let us move on to 7.3. So it says a standard solution of sulfuric acid with a pH of 0.22 was titrated against a potassium hydroxide. solution with an unknown concentration. Okay, so titration, you have a strong acid, you have a strong base, so you're going to get a neutral solution, right? The balanced equation for the reaction is as it is written over here. Now 7.3.1 says define the term standard solution. So basically a standard solution is a solution with a known concentration. Okay, so the thing about it is you have concentration that you know. All right, and then 7.3.2, calculate the concentration of the hydroxide ions in the standard solution of sulfuric acid at 25 degrees Celsius. So that's at room temperature. So what are we looking for? We're looking for the concentration of hydroxide ions. Let's check out the formula that we can use in order to get that. I hope you see that we're going to use Kw, where you have the concentration of hydronium multiplied by the concentration of hydroxide. Okay, and that being equal to 1 times 10 to the power negative 14 at 298 Kelvin. All right, so now let's go back to our question. So before we even get to hydroxide, we need to get hydronium. Okay, now we need another formula that I forgot to write down. So the pH. pH is equal to negative log. And then you have your hydronium ion. So for us to get the concentration of the hydronium ion, you're basically going to take the negative to that side. Okay, so you're going to have negative pH is equal to log of the concentration of hydronium. So the concentration of hydronium is equal to 10 to the power negative pH. Did they give us the pH? Yes, they did. They said it is 0.22. So 10 to the power negative 0.22. That will give us the concentration of hydronium. So let's do that quickly. And we get a value of the concentration of hydronium to be 0.603. I will just leave that value in the calculator and then go to the Kw equation. So it's basically 1 times 10 to the power negative 4 is equal to the concentration of hydronium multiplied by the concentration of the hydroxide. So the concentration of the hydroxide is equal to 1 times 10 to the power negative 4 divided by the concentration of hydronium, which is 0.603. So then what do we get as the concentration of the hydroxide? So 1 times 10 to the power negative 14 divided by the answer, we get 1.66 times 10 to the power negative 14, and this is concentration, so mole per cubic decimeters. Okay, and that's it for how many marks? 5 marks. Okay, that was a nice 5 marks. And then we get to 7.3.3. 20 cubic centimeters of sulfuric acid neutralizes exactly 30 cubic centimeters of potassium hydroxide. Calculate the concentration of the potassium hydroxide solution. All right, let me just have a look at the formula sheet again. Oh yeah, so we're going to use this equation over here where we have concentration of the acid multiplied by the volume of the acid over concentration of the base multiplied by the volume of the base, which is equal to number of mole. So you're going to have that mole ratio here. Okay, now do we have the concentration of the acid? We have the concentration of hydronium. Okay, so we can then use it to get the concentration of the acid. Okay, so on the side I will say concentration of the acid which is concentration of sulfuric acid, would be equal to the concentration of hydronium divided by 2. Remember, the acid we have H2SO4, so basically you are giving away 2 of your protons because it ionizes completely, and that is why we divide by 2. If it were another way, basically if it were H3PO4, which would dissociate completely, you would divide by 3, okay, and so forth and so on. So yeah, and then we did calculate the concentration of hydronium in the previous question, so that shouldn't be something that is too difficult to do. We had 0.603 divided by 2. We're going to get somewhere around 0.3015. Okay, so that is the concentration of the acid. So we're going to write there 0.3015. Okay, let's see. We're going to get 0.603 divided by 2. Okay, just wanted to make sure. And we're going to multiply by the volume. So the volume of the acid is 20 cubic centimeters. You can choose here to turn it into cubic decimeters, or just leave it because it will cancel ultimately. But I think in the spirit of just remaining constant, you can convert it to cubic decimeters. So you're going to have to divide by 1,000, so you're going to get 0.02. Concentration of your potassium hydroxide, that is what you're looking for. Okay, I'm actually gonna use potassium hydroxide there instead of just saying concentration of the base. And the volume therefore would be 0.03, and then that would be equal to, if I look at the ratio of your acid to your base, so that would be the acid to the base. Okay, now if I were to then get the concentration of potassium hydroxide, I would take the C over here and this 2 over there. So I now have 2 times 0.3015 times 0.02, and that's divided by 0.03. So let's calculate all of that. We have 2 times that answer times 0.02 divided by 0.03. And you get an answer of 0.40 if we're rounding off to 2 decimal places. And because we're dealing with concentration, it will be mole per cubic decimeters. Okay. And that was also, yeah, another 5 marks. Nice 5 marks. So let us see then, 7.4. All right, so it says an aqueous solution of ammonium sulfate was mixed in a beaker. Okay, a few drops of bromothymol blue were added to the solution. So in this case, this is a theory question, experiments that you could have done in class or not. Maybe you watched the video. But yeah, it's one of those experiments, okay, where you have ammonium sulfate, and then you add a few drops of bromothymol blue. Okay, normally you would use bromothymol blue if you want to titrate a strong acid and a strong base, okay, with a pH of around 7. So it's more, yeah, in the middle. Okay, so we'd use bromothymol blue, and it changes the color from yellow to blue, okay, at a pH of about 6 and 7.6. But anyway, in this case, you added bromothymol blue to the solution. So what is the expected color, right? So here, 7.4.1, you would expect yellow. 7.4.2, it says explain the answer in 7.4.1 by using a hydrolysis reaction. Okay, now let's work it out. You have sodium, so you have ammonium, okay? Ammonium, and so you have NH4. And if you're gonna separate these, you have to put ions to it, okay? So it has a charge of 1 there. And that is now in water because it's hydrolysis, okay? So you have to have water. And then it's a forward, also reverse reaction. Then you get, what is this? You get ammonia, which is your base, and hydronium. Okay, so that is basically what would happen over here. Okay, you have your ammonium, ammonium. Your sulfate here would be a spectator ion, so we're not really gonna put it there. And then you have water, so then it turns into ammonia and hydronium. Okay, so the solution then will be acidic, okay, and will be acidic due to the hydronium that you have there. All right, and because the solution is acidic due to the hydronium, then you would expect a yellow color. And yeah, that's it. That's it. 3 marks done. The paper is finally done. All the best with your chemistry on Tuesday, the 26th. Yeah, that's the 26th.